Hello, my name is Caio Vitorino and I'm a PhD student in electrical engineering at Federal University of Bahia in Brazil. This research was developed at the Robotics Laboratory of the graduate program in electrical engineering by me and Upiratã Jr. under the supervision of Professor Dr. Scolari and Professor Dr. Laser Schnittmann. This research is part of the development of Smart Robotic Additive Manufacturing Unit (SRAM), supported by FASTEM. This system is capable of recognizing and picking up parts without the need for human interaction. As you can see in this video, an AGV robot moves autonomously to a position close to the manufacturing unit to collect a 3D printed part. A robot manipulator picks up the part on the print pad and moves it to the AGV robot. After that, the AGV robot moves back to the initial position. This additive manufacturing unit must be safe enough for avoiding collisions with objects in the environment during the pick-and-place activities. As a solution to this, we proposed an improved path planning technique based on the artificial potential field algorithm. This additive manufacturing unit is responsible for recognizing an object, estimate its pose, grasp it using a vision-based control, and move it to an AGV robot. This is achieved by means of the pick-and-place skill that employs an object recognition system based on convolutional neural networks. In order to acquire reliable images for the object recognition system, the robot moves to a pre-grasped position before the pick skill. One of the goals of autonomous robotic systems is to perform safe movement control so there is no collision with obstacles such as people, machines, and objects. This objective requires the treatment of several problems such as perception, movement control, as well as trajectory and path planning. The Artificial Potential Field, or APF, first proposed by Professor Dr. Alsama Khatib, is an example of path planning algorithm that can be applied in real-time applications due to its local path planning and low computational cost. The manipulator moves in a force field. The position to be reached is in an attractive pole to the end effector, and the obstacles are repulsive surfaces to the parts of the manipulator. This path planning algorithm considers the element of the environment as electrical charge, in which the goal has the opposite polarity of the robot and the obstacles have the same polarity. Therefore, we can generate potential fields that act like the electrostatic field that attracts the robot to the goal and repel the obstacles. The generated potential fields reduce the path planning problem to an optimization problem. The potential field is the objective function and the goal represents its global minimum. The gradient descent algorithm is used as the optimization method. In order to avoid some singularities throughout the planning, the attractive field must reduce as it approaches the goal. This is required to obtain a smooth movement through the path. Be new at origin. It's crucial to stabilize the movement after the robot reaches the goal. Have continuous derivatives at the origin. This behavior is necessary because if you have its continuity at the origin, an impulse could be generated and serious damage can happen to the robot. Have constant derivatives for long distance from the goal. This prevents that the force increases unbounded far from the goal and causes excessive acceleration. Here we show two equations. The first one is the attractive potential field continuous function by parts. These functions represent a transition between a conic to a parabolic curve. Consider the parameter d, which is the attractive influence distance. In this equation, we calculate the Euclidean distance between the robot's initial and final position determined by the control points on each joint. The second equation shows the negative gradient of the attractive potential field. Note that as the robot approaches the goal, the attractive field remains constant if the robot is not within the attractive influence distance defined by d. If the robot gets too close to the goal, the attractive force will begin to decrease after a small increase. The repulsive field must increase as it approaches the obstacle, Approach infinity at the obstacle center, have a repulsive influence distance in order to avoid collisions with obstacles. Due to this repulsive influence distance, the robot starts to decrease its velocity before the collision with the obstacle. Here we present two equations. The first one is the repulsive potential field continuous function by parts. This function represents a transition from a zero potential to a potential that increases with the inverse of the distance to the obstacle. Consider the parameter ρ0, which is the obstacle's influence distance. The second equation shows the negative gradient of the repulsive potential field. Note that as the robot approaches the goal, the repulsive field increases to infinity at the obstacle center. Goals non-reachable with obstacles nearby, or GNRON, is the inability to reach the goal when it's within the obstacle's influence distance. The so-called modified artificial potential field, or MAPF method, solved the GNRON problem, but as the robot moves away from the target, the total repulsive field increases proportionally to the distance from this target, which is not desirable since it can prevent the robot from reaching its target. Zhang, Liu, and Chen presented the adaptive artificial potential field method that is an enhanced version of the modified APF that solves the GNRN problem and prevents the increase in the repulsive field. As opposed to the modified APF method, when a robot is far from the target, the repulsive field behaves similarly to the classic APF, therefore preventing the occurrence of local minimums. Close to the goal, the repulsive field behaves as the modified APF case, so the GNRN problem is avoided. In Figure 1, we show that the resulting force F acting on the robot avoids the obstacles and moves towards the goal. In Figure 2, the resulting force moves the robot away from the obstacles. As a result, it's not possible to approach the goal within the obstacle's repulsive influence area. The adaptive artificial potential field algorithm solves the GNRN problem by modifying the repulsive potential field. The workspace repulsive force has a component parallel to the attractive force, allowing the robot to approach the goal while avoiding the obstacle. It behaves in the same way as the classic APF when it's far from the goal. Here we introduce two equations. The first one is the repulsive adaptive potential field continuous function by parts. In this function, when the robot is far from the target, the adaptive APF method is equal to the APF classic method. The term n should be equal to for the function to be differentiable in the interval from minus infinity to infinity. The unit vector n sub r indicates the direction from the obstacles to the robot, and n sub rg denotes the direction from the robot to the goal. The frep1 component, represented by the first equation, repels the robot from the obstacle, and the frep2 attracts the robot to the goal. Note in this image that the frep1 component moves the robot away from the obstacle, and the frep2 drives the robot to the goal. The total force acting on the end effector will guide the robot to the target. The adaptive artificial potential field method allows the control point on the robot to smoothly enter the obstacle's influence distance. Therefore, we apply the classic APF method on the other joints except for the end effector, so there's no risk that the other control points will enter the obstacle's influence distance. Orientation control is really important in path planning. The end effector is sometimes required to be in a specific orientation in order to pass in narrow passages or pick an object in a required orientation without colliding with the surrounds. The adaptive APF method itself does not provide orientation control. That is, it's not possible to reach an orientation goal using only the adaptive APF method. In this figure, the robot tries to pick an object located on the print bed. Since the AAPF method does not provide any solution to control the end effector orientation, it's not possible to pick the object on the 3D printer. In this case, the end effector orientation is naturally changing over time in consequence of position control. The APF method was also implemented in configuration space in order to control the orientation of the end effector through the path. The attractive force is set to the negative gradient of the classic APF method in configuration space. Therefore, we do not consider the Euclidean distance to the target, but the Euler angles instead. This figure shows the robot-based link frame on the left and the end effector frame on the right. The end effector frame gets attracted by the robot-based link frame through the attractive potential field in configuration space. Therefore, the end effector orientation will continuously change over the path. For this method to work correctly, a static frame should be set as a goal. It could be the base link as shown in the image or any other frame created for this purpose. To implement the end effector orientation control, only the angular part of the Jacobian matrix is considered. We transform the attractive force of the orientation from configuration space to workspace through the transpose of the angular Jacobian. Note in figure 6 that the beginning of the three paths is equivalent as expected, since the adaptive APF method and the APF method behave similarly far from the target. When the robot approaches the obstacles at approximately 50 to 200 samples, the differences are noticeable. The proposed adaptive APF method with orientation control is the only method that converges to the goal compared to the classic APF method and the adaptive APF method without orientation control. In this experiment, we use the adaptive APF method with orientation control. The graphs shows the magnitude of the attractive force, repulsive force, and the judged angles over the path. The video shows that the orientation is smoothly changing to achieve the target orientation. The path remains smooth even when the end effector enters the repulsive fields, proving the efficiency in solving GNRON problems. In order to compare the results, we use the APF classic method with orientation control in this experiment. Note that the orientation changes over the path, but the robot does not reach the goal since the APF method does not solve GNRON problems. Furthermore, there are excessive oscillations around the repulsive fields. In this experiment, we use the adaptive APF method without orientation control. Note that the end effector orientation is only changing over the path as a result of the position control. In addition, when the end effector enters the repulsive field, it oscillates while trying to reach the goal. The robot does not reach the goal since the orientation is not adequate to pick the object on the print bed. In this research, we introduced a new end effector orientation control technique based on the adaptive artificial potential field, which allows the end effector to reach the desired orientation. The local minimum, known as goals non-reachable with obstacles nearby, was also avoided employing the proposed method. It was shown that the adaptive APF method reduces the oscillations in narrow areas and allows the end effector to reach the goal even if it's inside the obstacle influence area. Experimental results shows that the proposed method performs in practice as expected by the theory. Despite the results, the manipulator does not always reach the goal due to the static weights of the attractive and repulsive forces. Therefore, it's necessary to constantly adjust them in order to achieve a balance between the potential fields. In future works, a method for environment exploration with dynamic targets and obstacles will be applied. A object recognition system will also be implemented in order to relate each obstacle field to the objects in the environment. We'd like to thank Fasting for the financial support in this project. If you are interested, please see the experiment video on our YouTube channel called LAR Robotics Lab, UFBA. Thank you.